In this video, as promised, we're going to explore the connections between the function properties of injectivity, surjectivity and bijectivity and the different types of inverse which we met in our last video. So here's our theorem on left inverses. It says if f is a function with a non-empty domain, then it has a left inverse if and only if it is injective. So let's see how the proof works. For the if direction, we have to suppose that f is injective and prove that it has a left inverse. So we're going to construct that left inverse. So let's notice first of all that if you've got an element b of the image of f, then it's equal to f of a for only one a in the domain of f. The reason that's true is because if b was equal to f of a and it was equal to something f of something else, say a prime, so if this is true, well then f of a is equal to f of a prime, because they're both equal to b. But because f is supposed to be injective, a equals a prime. So if something is in the image of f, then it's equal to f of a for one and only one a in the domain of f. Using that observation, we're going to construct a left inverse to f. And here's how that construction goes. We pick at random any element of the domain of f, and we call it x0. Doesn't matter which one we pick, just any element in there. Then we define g from y to x by a definition with two cases. So at an input y, if y is in the image of f, then it's equal to f of a for one and only one a in x. So we define g of y to be that a. On the other hand, if y is not in the image of f, then we define g of y to be this fixed thing x0 in x. So that's our definition. And then I claim that actually g is a left inverse for f. In other words, g composed with f is the identity on x. And that's now easy to check, because if we take something in x, call it a, then g of f of a, well, what's that? We have to look at the definition of g. We're applying g here to something in the image of f, so we're in the first case of this definition. And the first case says that something equal to f of a should be sent to a. So here we have g of f of a, and it should be sent to a. That establishes that g composed with f is the identity function on x. Conversely, let's suppose that f has a left inverse, g, and we're going to show that f must be 1 to 1. So if f has a left inverse and g is such a left inverse, then g composed with f is the identity on x. To prove that f is 1 to 1, let's suppose that we have two things, a and b, in x, and that f of a is equal to f of b. Well, then we can apply g to both sides of that equation. So g of f of a is g of f of b. But g composed with f was the identity function. So what we have is just a is equal to b. We've proved that if f of a equals f of b, then a equals b. And that proves that f is 1 to 1. Now let's prove a similar theorem for right inverses. This says that if you have a function f, then it has a right inverse if and only if it is surjective. Again, we'll use x to represent the domain and y to represent the codomain of f. So this time the proof is a little bit simpler. We will take, for the if direction, what we're going to do is we're going to observe that for each element of y, so each element b of y, because f is surjective, there's at least one element which f sends to b. So maybe there are lots of them, but there's at least one of them. So for each b and y, we'll choose one of the elements which f sends to b, and we'll call that element that we chose g of b. Now that defines a function g from y to x, because for each b in y, we've associated an element g of b in x. And this has the property that f composed with g is equal to the identity on y. So the reason for that is that if you look at f of g of little y for some little y and big Y, well, the choice of g of y was something which f sends to y. So by definition, this is y. All right, now for the only if direction, we have to suppose that f has a right inverse and then prove that it's surjective. So let's suppose that f composed with g is the identity on y. Now pick b in y. I have to prove that f is surjective, so I have to show that there is something in x which f sends to b. But since f composed with g is the identity on y, evaluating both sides at b, I get b is equal to f of g of b. So b is equal to f of something in x. And that means everything in y is equal to f of something in x. In other words, the image of f is equal to y, and f is surjective. Okay, finally then, our final theorem on invertibility and function properties is that a function f has a two-sided inverse if and only if it is a bijection. We'll begin with the if direction, so let's suppose that f is a bijection. Well, if it's a bijection, then it's one-to-one, so it has a left inverse. Let's call that left inverse. Let's call g a left inverse to f. And it also has a right inverse. So let's let h be a right inverse to f. Now the thing is, we're supposed to show that f has a two-sided inverse. So the way we're going to do that is by showing that actually, in this case, g must be equal to h, so that g is both a left and a right inverse to f as required. And the reason that g must be equal to h is as follows. So first of all, let's observe that g is equal to g composed with the identity on y. You remember that when we first met the identity function, we observed that one of its properties was that if you compose any function with the identity, you just get the same function again. So g is equal to g composed with the identity. And because h is right inverse to f, I can replace the identity with f composed with h. So g is equal to g composed with, in brackets, f composed with h. But function composition is associative, so I can re-bracket this as, in brackets, g composed with f, composed with h. Now I know that because g is a left inverse to f, g composed with f is the identity on x. So I can replace g composed with f with the identity, and what I've got is the identity composed with h, and once more, that's just h again. Going through that chain of equalities, g is equal to h, so g is both a left and a right inverse to f. The other direction is much easier. If you have a function which has a two-sided inverse, then in particular it has a left inverse, so it's injective, and it has a right inverse, so it's surjective. And a function which is injective and surjective is by definition a bijection. Now, there's actually something stronger which comes out, or not stronger, but something useful in a different way, which comes out of the proof we did of the if direction of the last theorem. We showed that if g was a left inverse and h was a right inverse to a function f, then actually g was equal to h. In particular, if g and h are both two-sided inverses to f, then they must be equal. So if f is invertible, it has one and only one two-sided inverse. So that enables us to use a piece of notation to represent the one and only one inverse to an invertible function. And we use f to the power minus 1 to represent that two-sided inverse to the invertible function f. And let me just make one more comment, that if f is invertible with inverse f inverse, then also f inverse is invertible with inverse f, because it has a two-sided inverse, which is f. Okay, finally, let's turn to what's called the shoes and socks theorem. And I'm going to try and write down why this is called the shoes and socks theorem. So I'll read it out first of all, and then I'll explain why it's called that. It says if you have a function f from x to y and g from y to z, and they're both invertible, then so is g composed with f. And in fact, the inverse of g composed with f is f inverse composed with g inverse. So why is this called the shoes and socks theorem? Well, in the morning when you wake up, most of the time at least, you probably do the following two things. You put your shoes on, you put your socks on, and then you put your shoes on. It has to be that way round. So if we let h be the put on shoes function, and we let k be equal to the put on socks function, then in the morning you apply which composition is it? So we do k first. So we apply the function h composed with k to your feet. In the evening, you want to invert that composition of functions. You want to get back to where you started. So you need the inverse of h composed with k. And the inverse of h composed with k is you must take off your shoes first and then take off your socks. It's not normally possible to take off your socks and then take off your shoes, just as it's not normally possible to form the composition G inverse composed with F inverse in the context of the proposition at the top. So let's see why this theorem is true. And it's true just by chasing these compositions. I claim that a certain function is invertible. Well, I have to prove that by giving you a two-sided inverse. And in fact, the two-sided inverse is just stated in the proposition there, so we just have to check it really works. We need to check that the composition F inverse composed with G inverse really is a two-sided inverse to G composed with F. So in the proof here, I've done the composition on the right. G composed with F inverse composed with G inverse. Well, because function composition is associative, I can re-bracket that any way I want. And I re-bracket it by doing the F composed with F inverse first. But of course, that's just the identity function on Y in this case. So what we've got is G composed with the identity composed with G inverse. I've not even bothered bracketing this because I know it doesn't matter which way I bracket it because of the associativity property. Of course, composing with the identity doesn't do anything, so we can just drop it, and we've got G composed with G inverse, and that is the identity on Z. So the composition G composed with F, composed with F inverse composed with G inverse is the identity, and therefore F inverse composed with G inverse is a right inverse for G composed with F. But similarly, the exact same type of computation shows you that the other composition is also the identity, this time on X, and therefore F inverse composed with G inverse is a two-sided inverse for G composed with F, and G composed with F is therefore invertible. So one more thing before we stop is that this result applies to not just to a composition of two invertible functions, but to as many invertible functions as you like. If you can compose them, then you can find their inverse by composing their inverses in the opposite order. All right, maybe one more thing, which is there's another way to phrase this this result, or at least part of this result. We know that being invertible is the same as being a bijection. So we could give a kind of slogan version of part of this theorem, which would be that the composition of two bijections is again a bijection. That's another statement of this shoes and socks theorem.